All right. Hi, everyone. I'm Nia, this is Matt and Nithya, and we are electrical and computer engineering students from the College of New Jersey. We'll be talking about our senior project, which is the tele-operated rover for disaster navigation. So let's get started. So for table of contents, we just have our project motivation. Why did we choose this project? What is our intended application? And then our functionality, what are the main goals? And then we'll go into a subsystem breakdown of what are the main components and what the main stuff being interacting with. And then our results and conclusion, what do we have so far? And then what are our next steps? So for project motivation, our group was looking, when we were thinking of what we wanted to design our senior project towards, we were thinking of the impact of natural disasters and extreme inclement weather, which we are seeing more frequently as a result of climate change and other factors. Which can often cause a lot of damaged infrastructure, communications, just a few examples of this. And there's countless others, of course, but the few that we highlighted right now are the Japan earthquake and tsunami in 2011, which caused damage to a local nuclear reactor, which caused extensive damage. Hurricane Maria in 2017 in Puerto Rico, which caused damage to transportation, agriculture, and even the energy infrastructure. And then a 6.2 magnitude earthquake in Indonesia in 2021, which caused landslides, and hundreds of people were trapped under rubble for a period of time. So the key points that we want to highlight are that it's dangerous, time sensitive, and expensive to use human intervention right away when any of these natural disasters occurs. And we need a way to enter these dangerous zones to either locate people or offer first aid supplies, potentially deliver supplies while people are in a situation where they can't be evacuated right away, and even temporarily fix communications access to then talk to people who are in that scenario who need specific help. So our solution was to develop a teleoperated rover with live camera feed and semi-autonomous capabilities. And the image here is just a picture of the nuclear reactor from that, as you can see, caused like a really big explosion, and it was a really big issue back in 2011 in Japan. So that's kind of what we were thinking when we were with our project frame in mind.
All right, so for our project functionality, basically what we are working on is, this is our rover, our current prototype. We found basically in our lab actually a semi-built rover with these mechanical frames, and what it can do, it can handle semi-rough terrain. We tested it recently outside TCNJ campus on like kind of this rubble-like surface we have, as well as all the dry grass patches and roots and everything, and it was able to handle very rough terrain and be able to drive over that. And what we're doing is Matt basically will continue talking about this later in the presentation about how he and Nia were working on motor control algorithms in order for the rover to be navigated based on what I see from the computer vision, which is feedback of object detections and what is in the way of the rover. And we're gonna be implementing a GUI that will allow us to seamlessly control our rover from a remote computer, so that the user does not have to manually get access to the internals of the software in order to control the movement of the rover overall. And we're just going to be also discussing the flexibility of our programming and the functionalities of our software for this rover overall.
So this is just like diving into the system analysis of the electronics on the rover. The main brain of the rover is a Raspberry Pi. That's taking care of things like computer vision, as well as providing audio feedback to anyone in the vicinity of the rover. This is connected to an Arduino Mega via USB port. And the Arduino Mega is connected to motor drivers, which are connected to motors, and that is what we're using to like actually program the motor control algorithms to achieve like steering and rotating and various other types of movements. So in terms of diving into like how the software flows for our project, essentially what a user would do is they would take their PC and connect to the Raspberry Pi via remote desktop connection via an SSH connection. And then on the Pi itself, we have various Python libraries like PySerial, like the previous group, to actually communicate between the Pi and the Arduino, as well as tkinter, which is useful for developing GUIs. And then we also have OpenCV for computer vision purposes. And so, like I said, we're using PySerial to like send velocity commands and different commands to the Arduino Mega, which we have C++ motor control algorithms on. So that kind of shows like the flow of the software and how everything interacts with one another.
So for the main hardware of our system, these are just a few components that we're going to isolate. We're not going to get into like the mechanical frame. So we're choosing a Raspberry Pi, a microprocessor, which, as Matt explained, is going to be used for our teleoperation and computer vision capabilities. And then we were using the Arduino microcontroller, which is used for motor control. So the Pi talks to the Arduino, which is responsible for motor control, and then the Pi handles most of the high computing functionalities. And then this is the camera that we selected. It's the Maker Focus IR camera, and we're going to use it for obstacle detection and live data feed, which Nithya will get into later. We specifically chose this camera because it has night vision capabilities.
All right, so for the breakdown of computer vision, essentially what is going on with our system is that I'm using a data set called Rover, which is called the Common Objects in Context. It's a very big data set that can classify, I believe, up to 80 different classes of different objects like humans, pets, things in the lab. I've tested it. It's able to detect water bottles and like things like that, as well as rocks outside. So using that and using OpenCV and using something called convolutional neural network models that are pre-trained that allow for me to automatically, like basically convolutional neural network really simply is just a way of simulating kind of how you can classify different images, and it's able to identify which those images are, and using the object detection recognition, which is like if it sees something in a camera frame, it's able to basically kind of create these boxes and be like, okay, based on this object, using the neural network model, I can identify this as a dog, or that this is a mic, or something in the way. And that's kind of what we see here. So using all this is happening in the Raspberry Pi, and through the serial communication with USB connection I will have with Matt and Nia's motor controller logic is within my code. There's parts of it where I'm basically saying if I see an object on the certain sides of the camera, like in the center of it, left or right-hand side, then I'm asking the motor to go in the opposite direction so that it can avoid that obstacle. So then for teleoperated mode, essentially, I'm basically kind of nudging the left or right motor to move a certain direction so then the user can control it from there onwards. And this is just like a system breakdown of the pre-trained neural network model that is used for object detection for the computer vision. It's called YOLO. It stands for you only see it once. And that's basically the image is only fed once into the model and it never sees it again, like it's never used again, because it was already heavily trained. I'm not going to go into details. It's kind of a bit more technical beyond this. But basically, the camera sees when I feed of some image, it goes through the whole neural network models, all those layers you see, and at the end, object detection, it's able to kind of narrow down, okay, I see one thing in this current frame. And from there onwards, like I mentioned before, based on wherever the object is, I didn't have these images shown here, but from last semester, I was able to split the screen so that it's left, middle, and right-hand side. So then that way I can detect which part of the screen the object is and allow the motors to move from there.
Guys,
So for the objects that I think add to that over time or and or objects.
Yeah, so one thing that I was looking into earlier this semester or last semester was trying to add extra images and try to train that. But the only thing was our limitation was that we don't have servers currently available to us that I could run neural network models with images that we have from our like around TCNJ campus outside specifically and train the model on that. That's the only reason why I've been working with pre-trained data sets and trying to merge newer ones this semester. That's the only limitation for this project.
So yeah, we also are like beginning to develop a GUI just to make like interfacing with the rover pretty easy. So as I mentioned before, we like wrote these motor control algorithms. And really what they are, they're just like functions. So you could like pass parameters into these function calls in order to achieve steering or achieve rotating. So the diagram on your left is basically showing like the various movements that we wanted to achieve. So like, of course, like forward and backward motion, as well as like steering, as well as rotating about its center axis. So the bottom diagram kind of gives you an idea of like how these motions are achieved in terms of like the velocity of the wheels. So for instance, if you want to steer one way, we basically just make the wheels on one side spin faster than the other to like push it into a direction. And if we want to achieve rotation, we're essentially just turning the wheels on either side in opposite directions with equal magnitude so that it will like steer about its center axis. So to like kind of encapsulate that, we developed this pretty simple GUI right now where you could essentially just like click the buttons to achieve any of those movements, as well as like a stop button, obviously, to stop it. And we also have these boxes to specify like the speed at which you're driving, the speed at which you're rotating. So this was kind of better than our original method, which was like using the keyboard, since it allows you to kind of specify like speed and the rotation speed and whatnot. And it kind of just like is visually a little bit more appealing. So sorry. And then this is just like some terrain tests that we ran on different terrains, since obviously if we're using this in like a disaster situation, then there's going to be like a various types of terrains that would probably be moving on. So like you could see it on grass, concrete, and gravel. And ultimately we'd want to probably test it on like somewhat more rough terrain, since these are like pretty flat. So in the future, we're going to perform more tests on like using different types of surfaces as well as different like inclines and whatnot.
So very broad summary is we started with this kind of old mechanical frame that had been used for about 5 or 6 years in the engineering department. And just to build off of what Matt talked about earlier about like the differential drive system that we developed, as you can see, the frame that we were working with didn't allow for Ackerman steering because those are like fixed motor holders right there. So we kind of had to like adapt and modify as we needed. And we were able to develop like the first half of our requirements, which is pretty good for us. So a more professional summary is our current project status. We currently have tele-operated motor function, which is good. We have rotations using differential drive. We have a separate computer vision detection subsystem, which can do object classification, and we're working on having it be able to control the motors from right or left. We have a user-friendly GUI currently still in development, and we've got a overall robust mechanical system that can handle multiple terrains. So our next steps are to then, the first and most important one is to immediately integrate the motor and the camera subsystem. So how the full system works together. Ideally, we should be able to mount the camera on and have our teleoperated user navigate the rover. And then if a big obstacle is in the way, it should be able to handle that autonomously, which is why we mentioned that it's semi-autonomous and not fully. Which then leads into the full system testing with live camera feed and object detection. And the last, more sort of an aesthetic purposes, would be like case designs, because if you remember, the original intention of the project was to have a way that the rover could deliver materials. So we need to sort of, right now we have all of our electrical components just kind of thrown into the box because we're still doing testing, but we do want to develop an organization system where we can have all of our boards organized and have a small compartment where we could have maybe first aid supplies, emergency radio, something that it can hold something that it could then deliver to somebody who's trapped in a situation that needs to be like rescued, communicated with, etc. So that's sort of our full overall. If there are any questions, please let us know.
Thank you.
What would you do about
About doors. That's a good question.
We were kind of thinking that it would be most used outdoors. I'm not sure. We didn't really think about it in an indoor. We are testing it indoors actually, but we didn't really think about it how it would go through like a barrier like that kind of size. But like that's definitely an interesting idea. I don't know if we could have a rover that could just open a door.
I mean, perhaps we were thinking about like I mean, I don't know if we would have the time, but like I guess like a future iteration, we wanted to have like a mechanical arm on it. So maybe having a mechanical arm that has like the capability of like opening up doors and whatnot.
Or and it uses the autonomy to understand the area around it. I'm a little confused where the threshold is, where the user is.
Right now, we're thinking of having it. We didn't have, because of the scope of the project and the time frame, we didn't really want to go too in depth into the GPS feature. The Raspberry Pi does have like a GPS feature where you could give it coordinates, and ideally, if we wanted to be fully autonomous, we wouldn't need a teleoperated user at all. We could just feed it coordinates, have it use the camera to then just navigate. But because of the time constraints and the budget constraints, we decided to limit it to, instead of using the GPS feature, focus more on like having it be teleoperated so that the user could use the camera feed to then navigate the robot, which in our favor kind of does work out, because you can use a human could then use their logic to see where they want it to go instead of training a robot to figure out if there's people that need help versus something else. And the semi-autonomous is more just for if the user is unable to see something or is unable to detect something maybe in the distance, maybe Nithya's computer vision detection system could then like alert the user, maybe like Drawbox or something, and say like, hey, there's something approaching, something like that.
If the vehicle we use to disaster like fire hazards, is there anything to account for like extreme temperatures or different air pollutants that may damage hardware or support for like or whenever you just extinguish your
Well, I mean, we did, that was like one of our concerns, obviously, was like, if it was in these, like a radioactive area, or like you said, like a fire hazard, how it would like affect the electronics. So that's kind of why, so like, right now there are some, basically like a lot of the hardware is kind of enclosed in this box that we were hoping would provide some protection from it. But
Yeah, for the time being, we're kind of having it be like, after everything's happened, we'll send this rover in. But it definitely is for like a future iteration, if there's going to be like a more advanced project, it would definitely be like, we would research like engineering materials and see like what's the best structure to build this robot out of, and then enclose it so that it's fully protected from like water and pollutants and maybe even like fire, like stuff like that.
You mentioned having this consider actually for you. So that
Yeah, actually, so last semester, Matt was initially starting out with Pi Audio, which is a Python library to do audio commands. Like basically, we had a speaker hooked up to the Raspberry Pi, and he was able to try to like feed in files so that it could potentially like give out instructions to the user. And that's what I've been trying to also incorporate with computer vision. So when it's like as the rover is being semi-autonomous, like controlled, then that way if there is like people in the area and like the rover is approaching them and then letting them know that we're going to open it up for supplies or anything like that, that's like one of our additional implementations for the semester, that if everything goes smoothly, we'll be adding that on top of the functionality of allowing this teleoperated option of sending out these voice commands through our speaker.
and I was gonna say one other thing is like, we thought that it was important to have some sort of like audio feedback to people in the vicinity of the rover, like Nithya was saying. So originally that's why we did find this like Python library called Pi Audio, where you can kind of like you could like run different audio files through it. So we were thinking of like kind of creating different audio files for like different situations, and then maybe like depending on like the situation, it would trigger one of the files to be played aloud so that people like in the vicinity of the rover would hear it and kind of get some sort of information from that, and to like help them with like whatever the issue is.
Thank you.
Thank you.
Thank you.